Howdy folks, Mr. Reed here, and welcome to one more question. So we're still doing combinations of transformations. This one is going to be a graph-to-graph image, and we're going to look at the transformations that are going on to take us from F to G, and in doing so we're going to write an algebraic representation of what those transformations are. I'm going to consider this to be a medium level question, so if what you want to do is write an equation to go from one graph to another, you're in the right place. So let's get to it. Alright, so equation writing time. We got the two graphs. I wrote the generalized form of our transformational, notation, where I have g of x is equal to a onto f, and then bracket b onto x minus h, bracket plus k. So, that's all written down and ready to go. So what I usually do is I just start going left to right through the parameters. So the first parameter here is an A, so we're going to figure out if there's any vertical stretching and if there's a vertical reflection. So I usually pick up whether there's a reflection or not first. So what we really are doing is looking at the shape of the original graph and the shape of the new graph and seeing if there is a top to bottom sort of inversion of interesting features. So specifically, there's this neat little spot here where we go down to a point and then back up. But in the new graph, we go up to a point and then back down. That's the inversion I was talking about. So yes, there is a vertical reflection. So I'm going to put down that A is a negative value, whatever that value is. So we've taken care of the vertical reflection. Now we'll head over to vertical stretching. So what I usually do is I actually just consider the entire function as a whole and look for the size of the whole function from its uppermost value to its lowermost value. You can also look for features and look at how large certain features are. So for instance, I could size up this short arm over here and say it's 1 unit tall. I'm going to say that the whole function is 2 units tall. And to end with over here, my new function is going to be transformed so it's only 1 unit top to bottom overall. So it's only half as large, which means that the stretch value is a half, and our A value is actually the stretch factor. So I can actually put in that 1/2 right away, and that's good. So we're going to move over to B. So this is the horizontal stuff. First, I'm going to take a look and say, is this thing switched around shape-wise left to right? So my little feature again, the one that I pointed out last time where we have a little pit, it's on the left of the picture in my f of x, but my upward part that's associated with it is on the right in the new function. So there's actually been a horizontal reflection here too. So I'm going to put the negative to take care of that horizontal reflection. And next up, I'm going to assess if there's been any stretch. So the red function, the f of x function, is going to go from -2 to +3. So that's 5 units in terms of its side-to-side size. This one, the g of x function, goes from -2 to 8. So that's 10 units. Going from 5 units to 10 units, that's a stretch factor of 2 because it's 2 times as large. B's tricky though because it's not the stretch factor that's the same as the B value. The stretch factor and the B value are actually reciprocals of each other. So if it's 2 over 1, the B value is actually 1/2. So there we go, reflection on both through both of these axes, and actually stretch factor of 1/2 on one and 2 on the other one, which actually means that the parameters are 1/2 and 1/2. Interesting enough. All right, so once you go to do your translations, you might luck out. So I'm going to tell you about a real nice shortcut. If you have a point that is on the origin, you are in luck, because what you can do is say, that point doesn't stretch, that point doesn't reflect, it stays where it is. The only reason why that point is moving from where it is because of a horizontal and a vertical translation. So you just count over to the new spot, and you get your H, you get your K, you're done. If you have a point that's on an axis, so actually this point would work. I'm not going to use it. I'm going to do the hard method where you have to follow a point through its stretching. But if I were to choose that point, then I would be able to not worry about how horizontal stretches and reflections would go. So I'm going to be really silly, and I'm going to choose instead this point up here. So that is the one that's on the end of the horizontal I guess, section of this graph. So that would be associated on the g function with this point down here. So somehow the original point has to move on to that new one. However, before it moves on to the new one, it's going to go through the stretching and reflections that we've already defined. So it is currently up at a y value of 4. It's going to get bopped down to a y value of -4 by the vertical reflection. It's also going to have a vertical stretch of a half, which is going to bring us up to a y value of -2. That's kind of off graph for what I left myself with. That's okay. I'm just kind of like following it along for my own benefit. It really doesn't matter whether I draw anything there or not. So -2 right now. That would be what would happen after the vertical stretching and reflections. Horizontally, it is currently at an x value of 3. Have to be a little bit careful here. The b value is a half, which actually means that the stretch factor is 2. So it's going to go from a 3 to a 6, but it's also going to have a horizontal reflection, which puts us way over at -6. So I mean -6. I'm way off my graph at that point. But I have to then bring it from -6 to -5 to -4 to -3 to -2. So I have to go over 1, 2, 3, 4 units to the right. That means I have an h value of 4. I also have to go from -2 up to 0. So that would be 2 units up, which will be a k value of 2. This should be the right set of parameters, so I should be able to just copy down my generalized function and put the parameters in instead. So that would be g of x is equal to -1/2 f onto -1/2 again, x minus h of 4, and then plus k of 2. So that should be what the equation is for this one. Let's say I'm not sure about it though. What I should be able to do is take some other point and make it go through the transformation, and I should get the associated point in my new function. Actually, I wasn't going to do this originally, but I think I'm going to use a mapping notation. So that would be like x comma y maps onto 1 over b, which would be -2x plus h, ay, which is going to be -1/2 y plus k. And so if I choose this point here, which is at -2, 3, then my -2 value for the x is going to be multiplied by -2 in my mapping notation, so it'd be a +4, plus 4 would be 8. So it should have an x value of 8. Sure does. That's good. All right, let's go over to the y value. The y value for this point up here again is a 3. And if I follow my mapping notation, I'm going to multiply that 3 by -1/2. Yeah, it is -1/2. So that would be -3/2 plus 2 would be +1/2. +1/2 is where that is. So that's not an absolute guarantee that everything's gone right, but it sure would be really fluky for me to have come up with a transformation using a different point that also works perfectly for a totally unrelated point. I mean, it's part of the same function, but I could have drawn my function differently and everything would have to happen the same way. But the fact that it does transform onto my new one with a different point means I'm probably in good shape. So hopefully you found that one helpful. Like, subscribe, and as always, take care, folks.